Notice you have seen that before, and this, just to remind you and to congratulate you on how much work you have already accomplished, since we have covered all those 17 formulae from section A, mechanics, plus these. This section alone has about 55% of the formulae you are required to know and use for CSEC physics examination. From section B, we have already covered quite a few formulae from section B. As a matter of fact, we have covered all of these, 1 right down to 6. And now we will consider Formula 7 and its variations. How to find specific heat capacity of a solid or liquid using an electrical method. In the last video, we were using method of mixtures. Now we saw this formula before, from which we got M1 C1 delta theta 1 is equal to M2 C2 delta theta 2. We are going to look at this E here and find two other ways that we can substitute that E. And the first one is VIT, but since P is equal to VI, we can also substitute for this EH, which is heat energy, PT. V represents voltage, I is current in amperes, and T is time in seconds. So if we were to substitute Formula 7 in Formula 6, we will get these two versions here. That is to say, we take out that EH in the front there, and we put in either VIT or PT. So we have this version of that formula and this one here. Now, both of them have C there, and you would recall that C stands for specific heat capacity. Example 1. An electric immersion water heater rated at 85 watts was placed in a cup of water for 45 seconds. How much heat energy was added to the water? And we are to assume that no energy was lost otherwise. Let's write what we are given. We know that time is 45 seconds. We know that the power is 85 watts. We want to find the heat energy. We have a formula that says heat energy, EH, is equal to PT, so that we know P and we know T. All we need to do is substitute in this formula here, and we will find out how much heat energy was added to the water in the cup. So we substitute 85 watts for P and 45 seconds for T. We multiply that and we get 3,825 joules. But by now you know we cannot leave that answer as so many significant figures. We are only allowed 2 significant figures, 2 there, 2 there, so our answer can only have 2 significant figures. We have to round off at that 8. So we get 3,800 joules, and that should suffice for CSEC. But just to be on the safe side, since we are rounding off at the hundreds, we take half of that 100, which would be 50, and we can better express our answer as 3,800 plus or minus 50 joules. We look at example 2 now. An immersion electric heater was placed in a cup of water for 35 seconds when its voltage was 24 volts and its current 2.5 amp. How much heat energy was added to the water? Assume no energy loss. Now, this question is very similar to the one we just did, except now instead of having P, we are given V and I. So instead of using this formula here, instead of using this one here, we will use that one over there. So we know the time is 35 seconds. We know the voltage is 24 volts. We know the current is 2.5 amps. We want to find the heat energy. We have a formula that says EH is equal to VIT. All we now need to do is substitute the values we are given. 24 volts times 2.5 amps times 35 seconds. You work that out and you get 2,100 joules exactly. And that should suffice for CSEC exam. Again, though, just to make sure, since our uncertain digit is at this hundreds position, we take half of 100, and that would give us plus or minus 50. So our answer is 2,100 plus or minus 50 joules. We will write that for CSEC, even though this is correct as well. Example 3, and it will now get a little more complicated. An immersion electric heater rated at 85 watts was placed in a thick styrofoam cup containing 231 grams of water at 21 degrees Celsius. And it was turned on for 1 minute 45 seconds. Calculate, first of all, the change in water temperature and therefore the final temperature of the water. The specific heat capacity of water, C, is 4,200 joules per kilogram per degree Celsius. Assume no heat loss. So first of all, we write what we are given. We know that the power is 85 watts. We know that the mass is 231 grams, which we need to convert to kilograms. We know that the time is 1 minute 45 seconds, which we need to convert to seconds. We know the specific heat capacity of the water. We also know the original temperature of the water as 21 degrees Celsius. So now we will calculate the change in temperature. How much did the temperature increase? And then once we get that, we will add it to the original temperature to find the final temperature of the water. So we use the formula PT is equal to MC delta theta. We change the formula around to make delta theta the subject, and so we get delta theta is equal to PT divided by MC. We substitute the numbers we are given. We know the power, we know the time, we know the mass, we also know the specific heat capacity of the water. And once we work that out, we get 9.199 degrees Celsius. By now, you know that that answer has too many significant figures. There are 2 significant figures here, 3 there, 3 there, and 2 here. So our answer can only have 2 significant figures. So we will have to round off at this point here, which will give us 9.2 degrees Celsius. And that should suffice for CSEC. However, as I said, just to make sure, you can always write in the margin of error. Since we are rounding off here, that is the 1/10 position, we take half of the 1/10 position and we get 0.05. So our answer is the change in temperature is 9.2 plus or minus 0.05 degrees Celsius. That is one part of the question. We have found the change in temperature. We also need to find the final temperature. Well, if the temperature originally was 21 degrees Celsius and it increased by 9.2, we just add the 2 things. We add the change in temperature to the original temperature. That's 9.2 plus 21 degrees Celsius. And remember, this is addition and subtraction now, not multiplication and division. So we will have to round off at the highest position that we have an uncertain digit. And in this case, it will be in the ones position. So we get 30 plus or minus 0.5 degree Celsius. That would be the final temperature. Example 4, an electric immersion water heater was placed in a thick styrofoam cup containing 235 grams of liquid at 21 degrees Celsius. The heater was turned on for 3 minutes and 25 seconds at a voltage of 24 volts and a current of 2.3 amps. Calculate the specific heat capacity of the liquid if its temperature increased to 65 degrees Celsius. Assume no heat loss. So as usual, we will write down the data that we are given. So we know the mass is 235 grams carried to kilogram, 0.235. We know the original temperature is 21 degrees Celsius. We know the time is 3 minutes, 25 seconds, carried to seconds would give us 205 seconds. We know the voltage is 24 volts, the current is 2.3 amps, and we know the final temperature as well as 65 degrees Celsius. We want to find C. So we look at these two formulae that we have here, that one and this one, and we find that this one over here would be better for us to use because it has everything except the one thing that we want to find. So if we say VIT is equal to MC delta theta, and we make C the subject of the formula, which means that C is equal to VIT divided by M times delta theta. And delta theta, by the way, if the original temperature was 41 and the final 65, the difference between those would be 44. And so we have everything on the right hand side of that C, and we can just substitute the voltage, the current, the time, the mass, and the change in temperature. When we put all of that in our calculator, we get 1094.39 joules per kilogram per degree Celsius. Of course, we cannot leave that answer as is. If you do, CSEC will deduct a mark for having too many significant figures. So let us see. 2 significant figures, 2 significant figures, 3 significant figures, 3 significant figures, 2 significant figures. Our answer can only have 2 significant figures, so we have to round off at this point, and that would give us 1100 joules per kilogram per degree Celsius, and hopefully that should suffice for CSEC. But by now you know, we will just make doubly sure and write in our uncertainty. Since we were rounding off at the hundredths position, we will take half of that hundredths position, which would be 50. So it will be 50 more to 50 less. And so we can better state our answer as the specific heat capacity of that liquid is 1100 plus or minus 50 joules per kilogram per degree Celsius. And that is how you go about finding the specific heat capacity of a liquid using an electrical method. So this electrical method can be used to calculate the specific heat capacity of any liquid. Now let's turn to the matter of solid. For example 5, we will look at an adaptation of question 4B from paper 2 of the CSEC examination from June 2018. The setup shown at left was used to obtain data in order to calculate the specific heat capacity of a metal. And this is the setup. So if you look at it carefully, you have a metal block here. You have insulation around the metal block. You have a heater in a hole in the metal block. You also have a thermometer here in another hole next to the heater. You have a voltage source, the voltage across here, we will be told, and the current, we will be told. Now, this is not a very efficient way of doing this, but this was in the examination question. So we will look at it. And the reason simply is the temperature here, whatever temperature you take here, it will be assumed that that is the uniform temperature of this whole block. Now, if it were water and you stir it, as in the previous case, then yes, we can assume that the temperature is uniform. But with this block, this is not a very good setup. However, this is what we will work with. We are told that the switch was closed for 845 seconds, that the mass of this metal block that you see here is 5.3 kilograms, that the change in temperature is 50 degrees Celsius. So you're not given the initial and final temperature. You are told that the change in temperature is 50 degrees Celsius. The ammeter reading is 8.5 amps, that's the current, and the voltmeter reading, which is the voltage, is 12 volts. You are to use the data given above to calculate the specific heat capacity of this metal. That's what you're supposed to do. All right, so as I said, this is an adaptation of a question that CXC set for June 2018, paper 2, and it's part of a question. So this is the data that we have. This is example 5 we are looking at. We want to use the data up here to calculate the specific heat capacity of the metal. We have this formula here that says EH is equal to MC delta theta. We know that we can substitute for that EH, we could substitute VIT or PT. So let's see what we are given. We are given time, we are given mass, we are given change in temperature, we are given current, and we are given voltage. Now we can use this, but it would require changing VI into P. But it would be easier to just use VIT straight off as is. So VIT is equal to MC delta theta. We know V, we know I, we know T, we know M, we know delta theta. So we have one unknown here. We change the subject of the formula such that C becomes the subject of the formula. And then we substitute the values we are given, 12 volts, 8.5 amp, 845 seconds, that's this piece here, divided by the other piece on this side, mass, 5.3 kilogram, times 50 degrees Celsius. We put that in our calculator and we come up with this answer. By now you know that answer has too many significant figures. Unless told otherwise, apply the rules for multiplication and division of significant figures. You may be told to give your answer to the nearest whole number, or to the nearest tens, or to one decimal place. But if you are not told that, then we fall back on the default situation where we will apply the rules for multiplication and division of significant figures and write our answer accordingly. So this has two significant figures, two significant figures, three significant figures, two significant figures, one significant figure. So our answer can only have one significant figure. We will round off at that 3, and we can state it as 300 joules per kilogram per degree Celsius. Hopefully that will suffice for CSEC, but I always say, make sure. Since we are rounding off at the hundredths position, we will take half of that position. So it will be 50 less to 50 more than the 300. And we will write it as 300 plus or minus 50 joules per kilogram per degree Celsius. And this is how CXC would expect you to find the specific heat capacity of a block of metal. It's not quite accurate. There may be some errors, but this is what we will learn for now. So up to this point, we have looked at all of these 7 equations you see on the left here. We just have one more to do in this section. This brings us to the end of this video, Physics 14.